How's it going, guys? It's Ashton again, and this is exam 3, part B1. And today we're going to be deriving the equations for the mole fraction of water and water vapor and air, and then the temperature and water in a cooling tower. So right here I already drew out a picture for us, but we have a cooling tower with some hot water flowing in from the top and exiting as cold water. And then we have some flow of gas entering from the base, cooling the water at some temperature. And then we also have the gas or air leaving the top of the cooling tower. And we're saying that the top of the cooling tower is going to be our zero, and the entire length is going to be z with positive going in the downward direction. And then we are going to have a specific portion of said tower, or is going to be our dz, and we're going to be looking for the mole fraction of water. And then we also have some cooling packing material, which is going to have a specific, we're going to call A, with it's going to be our specific area, and that's going to be in units of meters squared per meters cubed. So to start, we're going to be creating we're going to be actually solving some heat and mass transfer equations. So we're going to start with our gas flow rate. So our gas flow rate is going to be in kilograms per second. So we're going to have our G for our gas flow rate is going to equal to the gas flow rate of our water vapor plus the gas flow rate of our air. And then we want to change this gas flow rate. We want the change in gas flow rate. So to do this, we're going to say that we have our G, and then we want it in terms of kilograms, or it's in terms of kilograms. We want it in terms of moles per second. So we're going to be multiplying our G by our mole fraction, and we're going to over our molecular average weight. And then since we want the change, we can signify that with a D. So we have our change in our gas flow rate times our mole fraction over our average molecular weight, and that's going to be equal to the negative mass transfer coefficient times the concentration of water at our surface minus the concentration of our water vapor farther away, so basically our air. And that's going to be, since we're looking at the cross-section area, we're going to be multiplying by the cross-sectional area times our specific area, and then with respects to change of position. And then we also want this in terms of our difference in flow rate in terms of our cross-sectional area. So we can multiply this side by A as well. And then you'll notice that these A's will actually cancel out, leaving us with our change in our gas flow rate times our mole fraction over our molecular average weight. Our average molecular weight is equal to, since the negative sign, since we're going in the opposite direction of our positive that we specified earlier, times our mass transfer coefficient multiplied by our surface temperature of our water less than the concentration of our water far away, multiplied by the specific area times our change in position. And then what we can do is we can actually assume that the gas flow rate over our average molecular weight is going to be some kind of constant, so we can factor that out of our change since it won't be changing. So we're going to be left with our gas flow rate over our average molecular weight times the change in our mole fraction equals the negative mass transfer coefficient times our concentration of our water at our surface minus the concentration farther away times our specific area multiplied by our change in position. And then we can also rearrange this equation in order to get the change in position with respects to our change in concentration, and then multiply by the inverse of this fraction over here to get that we have our change in mole fraction over the change in position equals the negative heat transfer or mass transfer coefficient times our concentration on our surface minus concentration further away times our specific area multiplied by the average molecular weight over our gas flow rate. And then what we can do is, using the Anton's equation, we can convert these concentrations, or this concentration at our surface, to the pressure. And then we can also transfer this concentration of our air or water further away from the surface. And then we want it to be in moles per meter cubed. So we can rearrange those equations to associate those directly. So what we can do is we can rewrite our equation up here. So we have our change in our mole fraction over our change in position is going to be equal to, we have our specific volume times our average molecular weight over our gas flow rate, and then times our mass transfer coefficient. And then since we're looking at the pressure or the concentration of water at the surface, we're actually using our saturated water pressure at TW, and that's going to be over RT, and then minus our, since we want it in terms of moles per meter cubed, we'll multiply our total pressure by our mole fraction, and that'll be also over RT. And then if you're looking at this, you'll notice that this is actually going to be the molar flux of water. So this term right here, so we can say that we have our molar flux of water is going to be equal to our mass transfer coefficient times our saturated pressure of water at TW over RT minus our mole fraction times our total pressure over RT. And we can plug this directly into our equation up here to get a final differential equation of the change of our mole fraction with respect to position. It's going to be equal to the negative specific area times the average molecular weight over our gas flow rate times our molar flux of water. Now with that equation, our first equation solved, we can actually go to and start deriving the equation for the change in temperature with respect to position. So I'll be right back. I'm just going to clear the board real quick, and we can start talking about the change in temperature of our water with respect to position. How's it going, guys? I'm back from clearing off the whiteboard, and now we can actually discuss the change in temperature of our water with respect to position. So to start off, I'm just going to be drawing in the zoomed portion of our DZ area, our position area. So we have our specific area A, and then we have below it we have our cross-sectional area with our capital A, and then on the sides we're going to have our change in position, so our DZ, and then this, since we're going down, we're going to call our Z positive, and then coming in we have our temperature of our water at the inward, and then we have our flow of water coming out at some temperature. And then going in, we have our temperature of our gas in, and then we have our temperature of our gas out. And what we're going to do is we can set up an energy or an enthalpy energy balance in order to solve this differential, or to create a differential equation. And the way we can start that off is by looking at our inlet side. So for our inlet, we're going to have our cross-sectional area, and then we're going to multiply that by our liquid flow rate in order to give us kilograms per second. And then we can multiply that by the heat capacity of our liquid water, and then we're going to times that by our change in our temperature of our water. And then since we're doing an energy balance, we can set that equal to our outlet of our enthalpy outlet. So we can set that equal to our outlet. And then for our outlet, we have to account for some things. We have to account for the liquid evaporating into the gas phase, and then we can also account for the energy loss of our the heat energy loss from the water itself. So what we can first do is we have our cross-sectional area times our liquid flow rate times the heat capacity of our liquid water times the difference in our temperature of our water. It's going to be equal to the cross-sectional area of our specific area times the cross-sectional area times the change in our position, and then we're going to multiply that by the heat of vaporization, or not the heat of vaporization, but the heat transfer coefficient from air to gas, and then that's going to be multiplied by the temperature of our gas minus the temperature of our water, and then we can subtract off that water that's being evaporated into the air. So we have our heat, heat of vaporization for our water times the molar flux of our water, and then that's also being multiplied by our cross-sectional area and our specific area, all multiplied by the change in position. And then since we can factor certain terms out, we can rewrite our equation to be, we have our cross-sectional area times our liquid flow rate times the heat capacity of our liquid, and then that's going to apply that change in the temperature of our water. That's going to be equal to our specific area times our cross-sectional area times the change in our position, and then we can multiply that by our heat transfer coefficient from air to water times our temperature of our gas minus the temperature of our water, and then subtracting off that water we're losing due to evaporation. So we have the heat of vaporization of our water times the molar flux of our water. And then looking at this, we see we can cancel out actually our cross-sectional area term because they're on both sides. And then if we look at this, if we divide by dz on both sides, we can actually get the change in temperature of water with respect to position, and then all we have to do is divide our left side and our right side as well by our liquid flow rate and our heat capacity of our liquid water. So then that gives us, we have our change in temperature of our water, and then over our change in position. My marker's stuck, I'm sorry. And that's going to be equal to our specific area over our liquid flow rate times our heat capacity of our liquid water, and that's going to be multiplied by our heat transfer coefficient from air to water to multiplied by the temperature of our gas minus the temperature of our water, and then subtracting off our heat of vaporization for water times the molar flux of water. And then this will actually be our second differential equation, and then this will represent the change in our temperature of our water with respect to position. So I'm just going to clear this whiteboard off again, and then we can get into our final equation where we discuss and evaluate, and not evaluate, but create an equation in order to represent the change in our temperature of our gas with respect to position. So I will be right back. How's it going, guys? It's Ashton again. I just finished erasing the board, and I also felt free to write down the two differential equations we found. The first one, which is the change of the mole fraction of water with respect to position, and the second one was the change in our temperature of our water with respect to position. And now we're going to be looking at the change of our temperature of our gas with respect to position. So the first thing I'm going to do is I'm going to draw out a nice little picture for us. And then what we're going to do is we're going to look at the enthalpy of our water coming in and the enthalpy of our water leaving. And then we have the enthalpy of our gas coming in and the enthalpy of our gas leaving. And then we also have our dz. And then what we can do is, since we know it's steady state, we know that the change in our enthalpy of our water minus the enthalpy of our gas is going to be 0. So that means we have our change in our enthalpy of our water minus the change in the enthalpy of our gas. It's going to be equal to 0. So the change of enthalpy of our water equals the change in enthalpy of our gas. So what we can do is, since we determined the change in enthalpy of our gas in the previous section, or the previous equation for number 2, when we determined the change in the temperature of our water with respects to position, we can actually first, by starting to find and writing down the change in enthalpy of our gas equation. So to do that, we have our change in our cross-sectional area times our gas flow rate in order to get kilograms per second times the heat capacity of our gas multiplied by the temperature of our gas. And then we have to do is, to account for that enthalpy gained from the water changing into a gas, we have to add in the heat of vaporization times our gas flow rate times our cross-sectional area, and then we want terms in moles per second, so we can multiply by the mole fraction over the average molecular weight of our water. And this will give us our enthalpy, our change in enthalpy equation for our gas. So now what we can do is we can set it equal to our change in enthalpy for our water. So we have the change in our cross-sectional area times our gas in order to get kilograms per second times the heat capacity of our gas times the temperature of our gas plus that energy gained from our water changing to vapor. So we have our heat of vaporization times our gas flow rate times our cross-sectional area times our mole fraction over our molecular average weight. And that's actually going to be equal to, we have our cross-sectional area times our specific area over times our change in position, and that's going to be multiplied by our heat transfer coefficient, was all going to be times our heat transfer coefficient times the temperature of our gas minus the temperature of our water, and then that's going to be minus our heat of vaporization times our molar flux of our water. And then what we know is actually that when we're distributing our change into our first two terms over here, we know that our AG, or our cross-sectional area times our gas flow rate, is going to be constant, so that won't have a change with it. And we also know that our cross-sectional area, as well as our molecular average weight and our heat of vaporization, as well as our term for our heat capacity of our gas, are all constants. They won't have any change to them, so we can actually factor those out when distributing our change. And then we also know that our cross-sectional areas are all going to cancel out. So what we're left with is we have our gas flow rate times our heat capacity of our gas times the change in temperature of our gas plus our heat of vaporization of our water times our gas flow rate over our molecular average weight, and that's going to be multiplied by the change in our mole fraction of water, and that's going to equal our cross-sectional area times the change in position multiplied by the heat transfer coefficient times the difference in temperature between the gas and our water minus our heat of vaporization times our molar flux of our water. And then if we divide by the change in position, we're actually going to be left with two differential equations. But when we do it, we'll notice something very interesting and cool. So we're going to divide both sides by dz, which gives us our gas flow rate times our heat capacity of our gas times the change in temperature of our gas divided by the change in position plus the heat of vaporization for water times our gas flow rate over our molecular average weight times the change in mole fraction over the change in position equals our specific area times our heat transfer coefficient times the temperature of our gas minus the temperature of our water minus the heat of vaporization of our water times the molar flux of our water. And then if you recall from the first equation we found, the first differential equation we found, dy over dz, or the change in mole fraction of water with respect to position, is already up there. So we can substitute that equation in, and then So what we can do is we have our, I'll rewrite that over here. So we have our gas flow rate times our specific heat capacity of our gas times the change of position of our temperature of our gas with respect to change position plus the heat of vaporization times our gas flow rate over our average molecular weight of gas times the negative cross-sectional area, or negative specific area times the molecular average weight over our gas flow rate times our molar flux of water. And you can see these things actually cancel out. So our molecular average weight of our actually cancels out and our gas flow rate actually cancels out. Then that will actually leave us with, we have our gas flow rate times our heat capacity for our gas times the change in temperature of our gas over the change in position plus a negative heat of vaporization times our specific area times our molar flux of our water equals our specific area times our heat transfer coefficient times the temperature of our gas minus the temperature of our water minus our specific area times our heat of vaporization of our water times our molar flux for our water. And if we add this to the other side, we see that these terms actually cancel, leaving us with our gas flow rate times our heat capacity of our gas multiplied by the difference in temperature, change in temperature of our gas times the change in our position equals our specific area times our heat transfer coefficient multiplied by the difference in the temperature of our gas times the temperature of our water, dividing both sides by our gas flow rate and our heat capacity of our gas. We have our change in the temperature of our gas is over the with respect to position equals our specific area times our heat transfer coefficient times the difference in our temperature of gas minus the temperature of our water over our gas flow rate times the heat capacity of our gas. And this is actually our third and final equation. So now with all that being said, we've solved for all three differential equations. And now what we can do is we can go to Python in order to import some values and actually solve these differential equations and put them into a graph, which we will all do and explain in part 3, or part B2, I should say. So I hope you guys learned something today, and I will see you in the next part of this video.
How's it going, guys? It's Ashton again. I'm back on the computer. And this is going to be part 3, or exam 3, part B2 of the exam, where we're actually going to use the differential equations we solved for in part B1 and actually apply them to a real-world situation with a cooling tower. So what I did so far is I imported some Python packages, as well as wrote the given equations for the problem, which I'll post right here. So those are all the givens for the situation that we were given for the cooling tower. And I also imported the Antoine equation for the saturated temperature or the saturated pressure of water at a given temperature. So that's all right here. So first we can go by starting off and saying the given information where you're, so to start, we have the heat transfer coefficient, which is 10, and that's in units of watts per meter squared times Kelvin. Then we have the gas constant, which is going to be 8.314 joules per mole per Kelvin. Then we have the density of our air, which is going to be 1.2, and that's in kilograms per meters cubed. Then we have the heat capacity of our air, which is 1,000 joules per kilogram per Kelvin. And then we have the heat capacity of our water vapor, which is going to be 2,000 joules per kilogram per Kelvin. And then we have the heat capacity of our water in a liquid form, which is going to be 4,190 joules per kilogram per Kelvin. And then we have our heat transfer coefficient, which is going to be 40,700, and that's in units of joules per mole. Then I wrote down the equation for our mass transfer coefficient, which is going to be our heat transfer coefficient divided by the density of our air times the heat capacity of our air. And then we're giving a specific area of 5 in the problem, and that's in units of meters squared per meters cubed. Then we have the molecular weight of our water, which is 18 times 10 to the negative third kilograms per mole. And we have the molecular weight of our air, which is going to be 29 times 10 to the negative third kilograms per mole. We also have the velocity, which is given to us as 5 meters per second. The liquid flow rate, which is 0.5 kilograms per meter squared per second. And then we're at standard temperature or standard pressure, so we're going to have a density or a pressure, of 101,325 pascals. And we're also given in the problem that we have a height of 20 meters for our cooling tower. So the first thing we're going to do is actually define our z-plots. And what that's going to do is it's going to allow us to plot our data later on. So we're going to have our z underscore plot, and that's going to be equal to our, and we're going to np.line space from 0 to our height. And then we want 20 points, and that'll just give us a graph of 20 individual points where we can plot our data on. The next thing we're actually going to do is we're going to import those temperatures that was given to us. So we're going to have our temperature of our temperature of our water feed, which was given to us as water feed, which was given as 70 degrees Celsius. So we're going to add on 273.15, and that'll give us in units of Kelvin. And then we have the temperature of our air feed, which was given to us as 25 degrees Celsius. So we're going to add on 273.15 in order to give us Kelvin. And the next thing we're going to do is actually get in, we're going to start by defining the mole fraction of our water in our air feed, because we are given that we have a relative humidity of 50%. So we're going to do 0.5 times the saturated pressure of our at the temperature of our water feed, or air feed I should say. And then we're going to divide that by our total pressure. And then next we're going to have our gas flow rate of our air. So that was going to be G air, and that's going to be equal to our pressure times our I'm sorry, I forgot to go to the next line. So we have our gas flow rate for our air, which is going to be equal to our pressure times the molecular weight of our air, divided by our gas constant times the temperature for air feed, and that's going to be multiplied by our velocity that we were given. So with all of those things defined, since I've been through this situation and problem before, and we're using an initial value problem solver, we're actually going to need some initial guesses. So first, for our mole fraction of our outlet, that's just going to be equal to our mole fraction of our feed multiplied by 1.1. And then for our guess for our temperature of our gas at the outlet, underscore guess, that's going to be equal to our temperature of our air feed multiplied by, or not multiplied, but we're just going to add some arbitrary number. We're going to add in 5. And then what else we're going to do is we're going to use a variable called sol later, and then we want to make sure that we're not going to assign any values to that, so we're going to say sol equals none. Invalid syntax. Oops. How about we do times 1.1. Alright, and with all those variables defined, we are going to start by creating an equation. So we're going to define our dy and then tw and then tg for the change in our mole fraction of water, the temperature of our water, and the temperature of our gas. And then what we're going to do is we're going to say that our independent variable is going to be z, since that's what we're controlling the height of our cooling tower, and our dependent variable is going to be v. And then since we're going to store into an array of data, we're going to say that the first component of our array is going to be equal to the mole fraction of our water. The second component of our array is going to be equal to the temperature of our water. And then the third component of our array is going to be equal to the temperature of our gas. Alright, so with those defined, we can now start defining our gas flow rate for our water vapor. So our gas flow rate of our water vapor is actually going to be equal to the mole fraction of our water divided by 1 minus the mole fraction of our water. And we're going to multiply that by the gas flow rate of our air, and then multiply by that the molecular weight of our water, and then divide by the molecular weight of our air. Next, we're going to have the average molecular weight, or not next, but not the average molecular weight. We're going to have our entire gas flow rate, which is going to be equal to the gas flow rate of our water vapor plus the gas flow rate of our air. And then we're going to define our average molecular weight, which is going to be equal to our gas flow rate of our air plus the gas flow rate of our water vapor. And then what we're going to do is we're going to divide that by the gas flow rate of our air divided by the molecular weight of our air plus the gas flow rate of our water vapor divided by the molecular weight of our water. And then from there, we also need to define our heat capacity of our gas. So we're going to have Cg for our heat capacity of our gas is going to be equal to the heat capacity of our air multiplied by our gas flow rate of our air. And then we're going to add in the gas flow rate of our. Add in our heat capacity of our liquid or water gas, or water vapor, I should say. So that was what I call that, Wg. Yeah, so heat capacity of our water vapor times our GW, so our gas flow rate of our water vapor, and we're going to divide that entire thing by the entire gas flow rate. Now with those defined, we can start looking at the differential equations we derived in an earlier section, or section B1, so the part right before this where I drew them all up on the whiteboard. So the first thing we need to find, though, is actually the molar flux of our water, and that's going to be equal to our mass transfer coefficient divided by our gas constant divided by the temperature of our gas. And then we're going to multiply that by the saturation pressure of our water at our temperature of our water. And then we're going to subtract the mole fraction times our pressure. And then with that defined, we can start by actually going into the first differential equation that I solved for, which was the change in mole fraction of water. And if you recall from that, that was negative specific area. And then we multiplied that by our average molecular weight divided by our gas flow rate. And then we multiplied that by our molar flux of our water. Then the second differential equation we defined was our change in the temperature of our water. And that was equal to our specific area divided by our liquid flow rate divided by our heat capacity for our liquid water, or water, yeah, our liquid water. That was a capital L, right? Yes. And then we're going to multiply that by our heat transfer coefficient times the temperature of gas minus the temperature of our water. And then we're going to subtract our heat of vaporization of our water multiplied by our molar flux of our water. And then for our final differential equation, we had the change in our temperature of our gas. And that was equal to our specific area times our heat transfer coefficient divided by our gas flow rate divided by our heat capacity of our gas. And then we're going to multiply that by the temperature of our gas minus the temperature of our water. And then what we want to do is we want to return those exact variables. So we're going to return dy dTW for the change temperature of our water and then the change temperature of our gas. Alright. dTg. And then since we know that our initial guesses aren't going to allow us to converge because they're not as accurate as they should be, we actually can create a second equation in order to determine the correct initial values that we need to use. And then we can do that using a root solver. But first what we're going to do is we're going to tab everything over in order to create our second equation. We're going to move it down the line. And then we're going to define our second equation as our convergence equation because we want to converge on the correct feed of our air and temperature, and our air temperature and mole fraction. So we're going to say converge underscore feed underscore air underscore t and then underscore y. And we're going to call our variable v2. And what we're going to do is we can say that the first component is actually going to be equal to our exit mole fraction of water. So we have our y exit. That's going to be equal to the first component of our array. And then we can define the exit temperature, or the exit of our gas. So exit is going to equal to the second component of our array. So v2, 1. And that'll allow us to actually converge on the correct values later. So now what we want to do is we can use that sol variable that we created earlier in order to set equal to our initial value problem solver and then solve the variables that we're looking for. So we want to do sol equals solve underscore IVP. And then what's going to say, it's going to want the function we're going to call. So we want to solve for dy, t, w, and tg. Oops, that's not what it's called. dy, t, w, no, tg. There we go. And it's going to ask for the span, and we want it running from 0 to the height again. And after that, it's going to ask us for the initial guesses. So for the initial guesses for our mole fraction, we want the y exit. And then we know that for our, we know the water feed at the exit, or the water feed entrance, which we called TW feed. And then we want the gas, temperature of our gas exit gas. And then what we can do is we can actually set the dense output equal to true. And this will allow us to actually solve the equation. If we don't, we run into an error. And then we do dot sol, and then we want to store them in the z plots that we created earlier in order to display them. So we can do z plot, and then we also want to return the values that we got for these. So return solution of solution, and then we want to do the array, so our 0th component, and then we want the last value, so we say -1, and we're going to subtract that is our initial feed, so our y feed, and then we also want to return from our array the 2nd component and the last value. And we're going to subtract our feed for our gas, or water, I should say. So, or no, our gas, which I called YA feed. YA feed. No. That's not, this is YA feed, because that's our mole fraction. And this is our TA feed. And then hopefully if you run that, we run into no errors. Fantastic. So now we're going to use the root solver in order to solve and get the correct initial values that we can use in order to graph our data, actually. So what we can do is we can do root, and then it's going to ask for the function we want, and then we called that function, we called it converge feed and air temperature water. Next it's going to ask for our initial guesses. So our initial guesses were going to be our y out underscore guess, and then our, what do I call it, T out guess? Yeah, TG guess. TG out underscore guess. And if we hit this, we run into an error. Yes. Let's see if we can troubleshoot, because you know part of coding is running into errors and then figuring it out with your minds. So let's see. Name true is not defined, because I spelled true wrong. That's always good. True. Haha. Haha. Yes, another error. So int object not callable. Converge y. Let's see. So I will be right back. I'm going to do a little troubleshooting to see what I went wrong here and use the old Google. So I'll be right back, and then I'll talk to you in a second. How's it going, guys? I am back, and I just realized the errors of my ways. I forgot the multiplication sign right there. And I'm going to think, I haven't tried this yet, but I wanted you guys to be here when I try to solve it. So let's see if that actually fixes the issues we were having. And it does. So with this being said, this means we can now use the data that it gave us from our root solver in order to correct those initial values. And now what we can do is with those correct initial values, those guesses that we created, we are able to actually plot the data. So now we're going to go to fig equals make underscore subplots rows. We're going to have 3 rows, one for each of our 3 equations, and then we're going to have 1 column. So that's going to allow us to create our subplot. And then we're going to do fig.add underscore scatter, and then we're going to say x is going to equal to our z plot. Our y is going to be equal to the first component of our array from our solution. And I also forgot to add in, we have to add in this global sol in order to call our solution equation that we wrote outside of our function. So I added in this global sol to allow us to basically to call it into our graphing. So when we're graphing it, it gives us the ability to display all the numbers that the equation gives us from this solving initial value problem. And then since this is going to be our y component and we're going to be graphing the mole fraction first, we're going to say it's the 0 component. And then we want all the datas. So we're going to put that colon in really quickly. And then we can do a name. We're going to name it. And this is going to be our h, or y, h to the mole fraction of our water. And then we're going to say row. We're going to say the first row, and then column equals 1. And what we can do is to simplify matters, instead of having to type out the entire thing over and over again, I can copy and then paste it 2 more times in order to get the other values we're looking for. So all we have to do is change the row to 2, and then this row to 3, and then when we rename this, we are going to call this one, this is our temperature of our water, or no, temperature of our gas. And this one's going to be the temperature of our water. And then since temperature of water, if you recall from our equation, we put it in the first component. So we're going to change, or the second component I should say, so we'll change that to a 1. And then for the temperature of our gas, we put it in the third component, so we change that to a 2. And if we hit Shift Enter, we should have a graph. And we do. But I don't like how that graph looks. So we're going to do fig.update underscore layout, and we're going to set the height, or the width, we're going to set it equal to 600, and then we're going to set the height equal to 900. Amazing. Look at that beautiful graph. So let's see if this even makes sense. So if you look at the graph, starting at the top of our cooling tower, we have an initial mole fraction of water that's very small, which makes sense because we only have a 50% humidity up there, and that's what our mole fraction of water is based upon. And then as we travel, or we have the greatest, we have our full flow of water up at the top, so that makes sense. And then we go all the way down to the base where it should be around 0. And then if we look at the temperature of our water, at the top of the column we see that our water is pretty hot, and then at the base of the column we see it gets cooled from our air. And then the temperature of our gas, at the top of the column we expect it to be hot because it's cooling all of our liquid water, and the water vapor is entering into it that's already hot and heating up that water. And at the base of the column we should expect it to be cold, and it is colder. So we see the rise and increase as we travel from the base of our cooling tower to the top where the air should increase, and we see that the water stream coming in comes in very hot but actually is cooled down because our airstream. So with that, this concludes exam 3, and I hope you guys learned something, and I hope you guys are now able to derive differential equations yourselves through problems that we see in day-to-day life, actually apply them to certain situations like this and be able to actually graph them as functions like we did today. And then even you can now correct your initial guesses based off root solvers. So I just want to say thank you guys for being with me this entire semester. I hope you learned something today, and I will see you in maybe a next video.